Everybody, I am excited to get into this. We're going to jump into it shortly, but I want to make two disclaimers. First, this is not a walkthrough, all right? So I'm going to try to explain some things, but I'm not going to explain everything, all right? I'm really just writing stuff down. And secondly, for this one, I did already write down my solutions on paper. Probably, I don't know if I'm going to do that going forward because it'll be a lot of stumbling in the dark, but that's kind of what I want. So let's get started with this first one here. Oh boy. Oh wait. Okay. So I'll just write PF. Yeah. We're gonna try and keep things short. All right. So I'm gonna say let A. Oh wait. Sorry. Alpha, beta be in the complex, and my complex symbol is like take it or leave it. Where with alpha, let's see, equals a plus bi. That sounds good. And beta equal to c plus di, comma, where a, b, c, and d are real numbers. Fantastic. Okay. So I'll say then alpha plus beta equals, so by this definition's at the beginning of the chapter, but basically to add complex numbers like this is going to be you sum the real parts. You sum the real parts, I meant to say. So it's going to be a plus c plus b, b plus di. Okay. Now observe. Okay. We're going to observe that beta plus alpha, I wrote this in a bad spot, is going to equal, well, if we do it just flipped, right? That's going to be b plus a. No, whoops, sorry. Already messing up. Wait, so we flip this. Yeah, c plus a, there we go, my bad, plus d plus b I. But that is going to equal a plus c plus b plus di. You may be asking why. Well, because these are real numbers, and real numbers follow commutativity. Wait, the commutative property. Let's say it like that. The commutative property for addition. And if you notice, this is the same thing as alpha plus beta. So we are done. All right. Next! Okay, next we got this one. And I don't want to write, I guess I should. Fine. There, I wrote it. All right. My goodness. All right. So, notice that alpha plus beta plus lambda. Don't make fun of my lambdas, okay? Well, that's going to equal, I should have, whatever. It's going to get kind of messy, but so I'm going to use brackets here. Okay. That's going to equal, I wrote this down because, just to make sure I didn't mess up. So that's going to be a plus c plus b, am I messing up already? No, b plus di. Yep. And all of this plus m plus ni. And so we're just going to use the definition again. So I got to go down this path now. Okay. So this is like our A. This is our B now. And this is a C and a D. All right. So if we combine everything together, what's going to happen is this. We're going to get A plus C plus M. Basically, the real parts are all going to go together. Plus B plus D plus Ni. Okay. That's not too crazy. Now notice that, and I'll be a little more strategic this time. I'll go down here. alpha plus beta plus lambda is going to equal, that's a plus bi plus bracket. Beta, let's see, beta plus lambda is just going to be, did I mess up? No, I didn't. C plus m, yeah, I should just look at this because that make it easier. So C plus m plus d plus n I. But that's just going to equal a plus c plus m, plus b plus d plus n I. And if you notice, that's exactly the same thing we got when we did alpha plus beta plus lambda. So we are done. Woohoo. Next! Okay, I really don't feel like writing it again, so we're just going to say alpha, beta, and lambda. Just repeat what we said in the top one, and it's going to be the same situation. Okay, so it's lazy, yes, but I don't care. So note that alpha, beta, lambda is going to equal, should I write it out? Oh yeah, this is the one. Oh, frick. It's okay. So that's going to be, let's do parentheses, a plus bi times c plus di, that times m plus ni, and then basically it's the definition at the beginning of the chapter again. Multiplying complex numbers, we can just do this. I mean, it works how you would think it would work if you know distribution, but technically I haven't proved that yet, so the distributive property. But okay, so this is going to be, here we go. Yeah, I'll use parentheses or brackets. So this is going to equal AC minus BD plus AD plus BC I all times M plus NI. And then basically if we, I guess it's kind of distributing, not really though, but we're going to, so this is our A, this is our B, this is our C, this is our D. So we're going to multiply this out again, and if we do that, we're going to get, and I'm going to just, should I do it for clarity? No, we don't need clarity here. So if we do this, we are going to get MAC minus MBD minus, I guess I don't need these, oh well, NAD minus NBC. I didn't need the brackets, whatever. Okay. Plus, this is going to look so disgusting, I'm sorry. Plus NAC minus NBD plus MAD, put this in parentheses, MAD plus MBC, right? Yeah, MBC. This whole thing is an I. Now notice, now observe that we need to do, yeah, so alpha, beta, lambda is going to equal A plus BI times C plus DI times M plus NI, which if we do this, we are going to get A plus BI times, I wrote it down, yeah, CM minus DN plus CN plus dmi. Okay, and if you do this multiplication, you are going to get, according to my work, which I have to trust here, you're going to get, I won't use brackets, ACM minus ADN minus BCN minus BDM plus, that's going to be gross again, plus ACN, ADM. This was at the corner. That BCM plus BCM. Minus BDN. Okay. Just to make this explicit, notice that this equals MAC minus. So I just rearranged that. We can remove this around because of real number properties and stuff. So BDM is MBD minus, this is NAD. I just realized this should not be a minus. I messed that up. My bad. Minus NBC plus, if we want to match this up, ACN is NAC. We can move this and rearrange it. NBD plus MAD. Yep, that's MAD plus MAD plus MBC. And that is the same thing as alpha, beta, lambda. So we are done. That one, I was a bit sloppy. Next! Alright, number 4, same deal here. So let's say, observe. That's a good word. Lambda times alpha plus beta is equal to M plus Ni. And I'm just going to go ahead and do this. So this is going to be, if we go ahead and do that, it's going to be A plus C plus B plus D I. And then if we use our definitions for multiplication, we are going to get the real part is going to be MA plus MC minus NB minus ND. That's the real part. Plus MB plus MD plus NA plus NCI. And we're going to leave that right there because we're going to now observe. Now, notice. So lambda alpha, I might be saying A instead of alpha, my bad, plus lambda beta is going to equal M plus Ni, A plus Bi, plus M plus Ni times C plus Di, which if we do these two multiplications, you're going to be shocked. You're going to be shocked, okay? Cut that part out. We're going to get MA minus NB plus MB plus NA I plus what? MC minus ND plus MD plus N. What the heck is that? I think it's a C. Yeah. Okay. And then we're going to combine the real parts and the imaginary parts. So that's going to be MA plus MC minus NB minus ND. That's the real part plus you guessed it. Okay, MB plus MD plus NA plus NC because of real number properties, and that's the same thing this is the same as this, so we are good to go. Next. All right, so number 5, I am going to say this explicitly again. So we're going to let alpha, we already know it's a complex number, so I'm just going to say equal a plus bi, where alpha, beta, a and b are in the real numbers, okay? So since a and b are real numbers, that means the additive inverses of a and b exist. So we can say since a, b are in the reals, negative a, negative b are also in the reals, and so we're going to let beta equal negative a minus bi. And this might be sloppy. I don't know if I can technically do this. Like, you could say plus negative b, but I'm just going to do it this way. If it's lazy, oh well. Okay. So notice alpha plus beta equals a plus bi plus negative a minus bi, which by the definition that's going to be a minus a, or plus negative a, but you get it. Okay, plus b minus bi, which is going to go 0 plus 0i, which equals 0. Okay, so beta exists to show it's unique. To show beta is unique, we're gonna pretend there's another one. Suppose there is another, I don't know if another is the best word, but I'm just going to say another beta 1, it's supposed to be beta, in the complex numbers, such that alpha plus beta 1 equals 0. Okay. So what we can do, well, this is the way I do it. There's actually apparently different ways to do this, because I was looking online at how other people are doing it, and the way I'm going to do it, I guess it's kind of the same, but I'll just show you the way I thought of it. So note that alpha equals alpha. I don't think anyone will dispute that. Okay. Well, also, this means alpha plus beta is going to equal alpha plus beta 1, because alpha plus beta is going to equal 0, and alpha plus beta 1 is also going to equal 0 by our assumption here. And since this is an equation, I'm just going to add beta. I'm going to add another beta to both sides. So I'm going to say beta plus alpha plus beta equals beta plus alpha plus beta 1. Okay, and we've already proven that complex numbers are associative. Well, yeah, that's all we really need, the associativity. So this means, well, I'll just put this so we can group them like this, right? Okay, but this is 0, so this is going to be 0 plus beta is going to equal 0 plus beta 1, and that means beta is going to equal beta 1. Okay, so it is unique, and we are good. So that's pretty cool. Next. Okay, I guess I'll say it this time too. So let alpha equals a equal a plus bi, with a not equal to 0 and b not equal to 0, and yeah, so a and b are real numbers. Okay, I'll just say it in case somebody gets mad. They are real numbers. Okay, now I'm gonna make an inspired choice. Okay, I'm gonna say let beta equal 1 over a squared plus b squared times alpha minus, sorry, not alpha, a minus bi. Now, if you don't know where this came from, basically, well, look, I guess I can explain. So, look, intuitively, we're gonna think alpha should be 1 over, beta should be 1 over alpha, right? So, if alpha was a plus bi, just generic, then, and I don't know, I guess you just already have to know how to do this, but basically, if we conjugate it, or if we multiply by the conjugate, if you do this, you're gonna get this situation up here. Okay, so that's where that comes from. So yeah, okay. So notice that alpha times beta equals a plus bi times, and I guess this is a scale, like, really this should be with both of these, but I guess I'm being a little bit lazy here. Oh no, I wrote it out like that anyway. Alright, well, so look, if you just distribute this, you can do that. So this is going to be a over a squared plus b squared minus b over a squared plus b squared I. Okay, and if we multiply these, what are we going to get? We are going to get a squared over a squared plus b squared plus b squared over a squared plus b squared. Okay, that's the real part, plus yeah, negative ab over a squared plus b squared plus ba over a squared plus b squared I. Okay, and now I don't want to do it out, but basically, look, if we combine these, we're going to get a squared plus b squared all over a squared plus b squared, right? So that's going to be 1. And we know a squared plus b squared is not going to be 0 because these are real numbers, right? So we don't have to worry about dividing by 0. So this is just going to equal 1 plus negative ab plus ba. Those are going to cancel each other out, so that's just going to be 0i, okay, which equals 1. So, sorry. So that part's done. Now the uniqueness part, we're going to kind of do the same thing. So we're going to say, suppose there is another beta 1 in the complex numbers such that alpha times beta 1 equals 1, and we're going to do the same thing basically we did for the last one. So we're going to say notice alpha equals alpha, and also alpha beta is going to equal alpha beta 1 because these both are going to equal 1 by our assumption here. And I'm just going to multiply both sides by beta again. Beta alpha beta equals beta alpha beta 1. And again, you can group these together, right? And because complex numbers are commutative, which we proved earlier, or sorry, actually it was an example. Complex numbers are commutative. That was an example that proved that. So if alpha beta and alpha beta 1, if alpha beta equals 1, then beta alpha also equals 1. So it's going to be 1 times beta equals 1 times beta 1, which means beta is equal to beta 1. So they're the same thing. All right, and we are done. Next. Okay, something a little bit different here. So I might be a little lazy on this one, but yeah. So basically we got to cube this thing, which means we're doing minus 1 plus square root of 3i over 2 times, yeah, just, why'd I put a parenthesis there? Oh my goodness, that's disgusting. Over 2 times itself 3 times, right? So oh yeah, I'm not really going to use words because it says show, but I'm being informal. So I'm going to be lazy, so we got 2 times 2, so I'm going to pull out that 1/8. So that's going to equal 1/8. And then we got to do the top 3 times, which, if we do that, well, okay, let's do these two first, okay? Negative 1 minus 3 plus, we're going to get 2 negative square root of 3i's, so plus, or I guess I should, yeah, let me just do this, minus 2 square root of 3i. So all that times another, let me use a parentheses, times another negative 1 plus square root of 3i. And then notice that this is just going to be, oh snap, whoops, this should be 1. My bad. So 1 minus 3 is negative 2. And that's all we can do really. So this is going to equal 1/8 times, if we do this again, you got negative 2, so we're going to get 2 plus 6 plus, we get a 0 here. Let me just make sure that makes sense. So boom, boom. Yeah, okay, yeah, these two are going to cancel out, and then you're going to get 2 times 3, which is, oh, that's this, right? Okay. You're going to get this, okay? You're going to get this. And that's going to equal 1/8 times 8, which is 1. Okay, so good to go, good to go. Okay, number 8. This one, this is an exploration, okay? So basically what we want is we want a plus bi times a plus bi. We want some complex number times itself to equal 0 plus 1i, right? That's what I is, and this is going to be important later. So if we multiply this out, we're going to get the real part is going to be a squared is plus b squared. Wait, minus b squared, my bad. Minus b squared. I mean, I wrote this down. I guess I could just look at that. A squared minus b squared plus 2ab, I'll do it like this, I, okay, equals 0 plus 1i. So if we match the coefficients, we know we're going to get two things. So a squared minus b squared has to equal 0, and 2ab has to equal 1. So I'm going to solve for a here. This means that a would have to equal 1 over 2b. And so we're going to plug that in over here. We're going to put this into this. So we have a squared, or actually, oh, well, I solved for a. So I guess so a, that's 1 over 2b squared minus b squared equals 0. I'm going off the paper for this one, that's why. I'm multiplied by negative b squared. So I'm going to get, this is going to turn into b to the 4th minus 1 over 4 equals 0. Yeah, okay. We're going to get the same situation anyway. I just used a, which would probably been the easier choice. But we're going to do a difference. I'm going to do a difference. I mean, it's probably, I don't know. I'm going to do difference of squares. That's how I did it. So that's b squared. All right, I messed up terribly. So if we do a difference of squares, this is going to be b squared plus 1/2 times b squared minus 1/2 is going to equal 0. And so we're going to get, this can't really do anything with, b squared plus 1/2 times b plus 1 over square root of 2, b minus 1 over square root of 2 equals 0. And, okay, so look, b cannot be, well, actually, yeah, this is just always going to be, this part can never be 0 because of the square part. So b squared is always going to be positive plus a positive. That's always positive. So really, the only way this could equal 0 is if one of these two are 0. And so this means that either b is going to equal plus or minus 1 over square root of 2. And we know that a is going to be 1 over 2b. So a is going to equal 1 over 2 plus minus 1 over square root of 2, which is going to be 1/2 times the square root of 2 plus minus, which is going to equal plus minus square root of 2 over 2. Okay. And well, really, a and b, the signs are going to match. Okay. So our two solutions are going to be, and I guess I should say, square root of 2 over 2 is the same thing as 1 over the square root of 2. So these are equivalent. You could, if you radicalize this, you'll see that. But anyway, so our two solutions. Number 1 is going to be the complex number 1 over root 2 plus 1 over root 2i. And the second one is going to be negative 1 over root 2 minus 1 over root 2i. Yeah. Next. So these are going to be lists in R4. So solution. So first thing I'm going to do, I'm going to subtract this list right here from both sides. So we're going to get 2x is going to equal, so we just subtract the corresponding thing. So 5 minus 4 is 1, 9 plus 3 is 12, negative 6 minus 1 is negative 7, 8 minus 7 is 1. Okay, so 2, this is a list, so this is really 2 times x1, x2, x3, x4 equals this list again, 1, 12, negative 7, 1. Okay, because this is a property, or this was a definition, basically, or a proof. I think it was a proof. It was an example, but basically when you have a scalar like this, you can just distribute it to each of these things. So this is going to be 2x1, 2x2, 2x3, 2x4 equals 1, 12, negative 7, 1. And then basically, look, you just match these things up. So this means our list is going to have to be, so 1/2, 6, negative 7/2, and 1/2. So all we're doing, I'm just dividing each of these things by 2, basically, right? All right, well, that was pretty easy. Let me switch papers. Okay, this one is going to be a bit of a doozy, maybe. All right, so we're going to say, we're going to let lambda equal a plus bi, a and b, let me write it like this. A is in the reals, and b is in the reals. Okay, so basically, look, we can distribute this lambda to each of these things, all right, because it is a list. And so if we do that, we're going to get 3 things. We're going to get, and I'm going to go ahead and distribute all these things. Okay, we're going to, all right, so we're going to get these 3 expansions. And so if you noticed, the real parts are going to have to correspond with the real parts in this list on the right side here. So that means 2a plus 3b has to equal 12. 5a minus 4b is going to have to equal 7, and 5a, and negative 6a minus 7b is going to have to equal negative 32. Okay, and basically you can solve this system. You can use elimination or substitution or whatever, but if you do it, you're going to get that a equals 3 and b equals 2. Okay, and you can check that. That does work. I used elimination to do it. So these 2 values make this system hold. Okay, but that's going to be a bit of an issue. Okay, and I'm going to go to the problem one right away. Okay, so also from these, we see down here 7a minus 6b. That goes with this third list. So 7a minus 6b is going to have to go with is going to have to equal negative 9. Okay, so 7a minus 6b is going to have to equal, what did I say? Yeah, negative 9. Okay. Now, since this is a system, like the a and b are the same, right? So if we plug in a equals 3, b equals 2, it should work. Okay, so let's see what happens. So 7 times 3 minus 6 times 2. Here we go. It's 21 minus 12, which you may notice is not going to equal 9. Okay, it's going to equal 9. Oh, sorry. Whoops. It's not going to equal negative 9. Okay, there we go. So it's not going to work. Okay, and that's a problem. So this is going to be an inconsistent system, because really there's 6. This is a system of 6 equations with 2 variables. So a and b, a has to be 3, b has to be 2 for the real parts to work out. But if that's the case, then the imaginary part's not going to work out. So that's the issue. Cool. Next. Okay, so this one I might be lazy again, but we're going to say let x equal. We know x, y, and z are on this field, right? So we're going to say x equals x1 ... xn. I guess each of these are just members of the field, so just keep that in mind. y equals y1 dot 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 yn and z equal, you guessed it, z1 dot 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 zn. All right. What the heck was I doing? Oh, that was part of the other one. Ah. Okay, so let's see. So let's look at, so x plus y plus z is going to equal, so list addition was defined in the chapter. So basically you just add all these elements, like x1 and y1 are going to go together, and x, each xi is going to go with the yi. So this is going to equal x1 plus y1 dot 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 xn plus yn plus z1 dot 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 zn, and we're just going to combine those again. So that's going to equal x1 plus y1 plus z1 dot 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 xn plus yn plus zn. Boom. Okay, now we're going to observe x plus y plus z is going to equal x1 dot 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 xn plus y1 plus z1 dot 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 yn plus zn, and pretty much we can just do the same thing, right? So this is going to equal x1 plus y1 plus z1 dot 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 xn plus yn plus zn. And hey, that was the same thing. So both of these equal the same thing, so they equal each other. Boom. Next. Alright, this one, a and b are just scalars. So we're going to note abx is equal to ab times x1 dot 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 xn, which equals, is going to equal, because it's a scalar, abx1 dot 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 abxn. Okay, now notice that abx is going to equal a times bx1 dot 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 bxn, which equals, we just multiply by the scalar again, it's going to be abx1 dot 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 abxn. So they equal the same thing, and we're done. Boom. Next. Alright, so 13, honestly, I might not even, this might not even be right. Well, some of these might not be right. I mean, I think I got them right, but this one, it seems too obvious, so we're going to see. So I'll just write it down. So 1x is the same thing as 1 times x1 dot 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 xn, okay, which is the same thing as 1 times x1 dot 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 times, or comma 1 times xn. Okay, but 1 times x1, that's just, each of these xi's are from a field, so that's just x1 dot 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 xn. Okay, and that's just x. So I mean, they're really, it's not too crazy, right? Next. All right, this one is also not too bad. So we're gonna say note that lambda x plus y. I'm kind of skipping some steps, but this is gonna be x1 plus y1 dot 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 xn plus yn, right? So this is gonna be, well, I guess I'll write that. So this is gonna be lambda x1 plus y1 dot 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 xn plus yn. Okay, and that's gonna be, so this new list is, or this list is gonna be lambda x1 plus y1, whoops, dot 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 lambda xn plus yn, and because these are from a field, well, and lambda is from a field, right? We can distribute. So this is going to equal lambda x1 plus lambda y1. My lambdas are getting progressively shorter. Dot 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 lambda xn plus lambda yn. But we can use the definition of list addition again to kind of to separate these out. So this is the same thing as lambda x1 dot 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 lambda xn plus lambda y1 dot 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 lambda yn, which is just, I guess, this is more in depth than I went on my paper, but this is going to be lambda times x1 dot 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 xn plus lambda y1 dot 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 yn, which is just lambda x plus lambda y. Okay, so that one's pretty good. Nice, nice, nice. Last one. All right, last one here. A and B are just some scalars, or no, just some. They're field numbers, all right, and X is a list, all right, or they're just basically regular numbers, and X is a list. So let's see. So I need a better word. Behold. There we go. Behold, A plus B X is going to equal. So I'll write it out fine. X1 xn, which is going to be, I'll use big parentheses, A plus B x1 dot 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 A plus B xn. Okay, but these are just numbers, right? So we can distribute. So this is going to be A x1 plus B x1 dot 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 A xn B xn, which we can say again. So this is going to be A. All right, well, look, I don't really want to write it out, but you can see what's going to happen, right? We can separate them. It's going to be ax1 dot 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 plus a plus bx1 yada yada yada. We're going to split those up, right? So basically, we're going to get this ax1 dot 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 xn plus b x1 dot 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 xn, which equals ax plus bx, right? So sorry if you didn't like me skipping that, but fine. Look, okay, fine. So this is going to be, we can separate this as a x1 a xn plus b x1 b xn. Okay, and then just take the b out. We can factor out the a and the b. There's a step I skipped. Okay, yeah, happy? Good. All right, well, this was pretty fun. Yeah, and like I said, if there's any mistakes, please let me know. It could definitely happen. But yeah, thanks for watching. Oh, I would want to say, I'm going to try, how can I get my next video age restricted? What do I have to say in the first 10 seconds? Please let me know, because I want to try it out. So, yeah. All right, for real, bye this time.